Hello the internet and welcome back to my channel. Today on the bench we have a power computing power supply, and this belongs to a power computing system, and precisely a Power Center 132. This is of a friend of mine. He's got the system, he's got the power supply is not working, and rather than replacing it with a standard ATX power supply, because this is a standard ATX power supply, he would like to keep the one with the label that says power computing. Now, obviously, one option would be to replace the guts of the power supply with something different, but he asked me to take a look, so I would say, let's take a look. This video is sponsored by PCBWay. PCBWay offers PCB manufacturing for all your electronic needs. The service is very easy to use. Just go to PCBWay.com and upload the Gerber file of your project. The system will prepare it automatically, but you can tweak the parameters yourself. There are plenty of shipping options to suit your needs. I've used PCBWay for some previous projects, and I was really impressed by the manufacturing quality of the PCBs. The link is in the description. Thank you PCBWay for helping the channel, and now let's go back to the power supply. Right, I do not know what's wrong with this power supply, I only know that it doesn't work, so before I touch anything I'd like to test it, but before I test it I'd like to clean it, as it's not in the greatest shape. So let me quickly remove the dust and then we'll test it together. This is a standard ATX power supply. Mains is coming here, going through some filtering and into the bulk capacitors. The main switching MOSFET is on this heatsink, controlled by this IC here. This is the main switching transformer, while this little one here must be the one always on to generate the 5V standby used to power up the motherboard's logic to allow it to respond to the on-off button and in turn to switch on the power supply. This physical gap on the PCB is the separation between primary, where high voltage leaves, and secondary, where only low voltages are allowed. The only components allowed to cross the sections are those which don't create a physical electrical link between the two: transformers, optocouplers, and safety capacitors. This is to prevent high voltage to accidentally travel to the secondary, destroying your computer and also posing a risk to the user. Before I do anything to this power supply, let's test it to see what's wrong with it. As usual, I connect unknown equipment to my current limiter to avoid catastrophic events. As I said, this is a standard ATX power supply, so to actually turn it on, I will have to short the green wire to ground. My AT extension loom has a convenient rocker switch to do that. But when I apply mains power, the power supply is switched on by itself, even though for a brief moment. I could see the fan spin and the fluke recorded some voltage on the 5V line. Well, that shouldn't have happened. A power supply should not switch on unless, it's switched on. So right off the bat, there's something not right here. As a quick test, 5V standby is working as expected, so mains is definitely getting into the unit. So I did a quick visual inspection looking for something obvious, and that worked. This component here seems a bit toasty to me. There is another one behind the capacitors. Also, the glue around the capacitors seems to be the type which gets conductive over time. When I apply mains, my thermal camera reads temperatures over 100 degrees Celsius, which cannot be right for an electronic component. Let's remove the board from the case and take a better look. Looking at the back of the PCB, this is where mains is coming in, and here is where the bridge rectifier is. I have marked the capacitors, which are installed in series between ground and positive rail. The baked components are here and look like bleeding resistors, as they are in parallel with the capacitors. Their purpose is to slowly discharge the capacitors when mains is removed, otherwise the capacitors would stay charged for a long time. They're basically consuming power all the time, so it's okay they get warm, but should not bake to death. Let's take the resistors out. Yes, very much baked. I managed to peel off the heat shrink and the resistors are identical. The code is a bit cryptic to read, as it often happens, but surprisingly the resistors are still alive and read 22 kilo ohms on my multimeter. Now, I would like to know what voltage there is across those resistors so I can calculate the wattage they have to dissipate. I think I can power up the board with them removed. The only downside is that the capacitors won't discharge quickly. 491 volts across the positive rail from the bridge and 240 volts across the resistors and also each of the capacitors, that does not make sense. Rectified 240 volts mains should give 340 volts DC. With a PFC, or power factor correction, I would expect up to 390, not 491 volts. A 22 kΩ resistor fed with 241 volts DC will have to dissipate 2.64 watts. This is Ohm's law. Those looks like 2 watts resistors. That might explain why they're so toasted. Also, and this is scary, the capacitors are only rated 200 volts each, and I'm feeding 240 volts DC to them. They could explode. At this stage, I assumed a reading error on my multimeter for whatever reason, so I ignore the issue, but you don't want to feed more voltage than the rated voltage to the capacitor. Anyway, I'll move on for now. Well, I'm not expecting the resistors to be the cause of the issue, and indeed the power supply behaves as before, with them removed. Let's focus on the switching controlling IC. It's an FA5304. The IC would be responsible for stopping the voltage generation if something is wrong, so it's where I want to focus my attention. First, let's make sure there is supply voltage. And there is, I'm reading 11 volts, which is perfectly fine. Then let's check the output. I see a momentary waveform, which makes sense, we do have some voltage, but then it stops. I then checked the overload pin, but I might have misunderstood the datasheet, as it turned out that in order to detect an overload, the IC is expecting at least 0.24 volts, and my scale on the oscilloscope was set too high when I checked, so I might have missed something here. To check why the power supply turns on regardless of whether it's told to power on or not, I checked pin 8, where I found this intermittent signal. And again, I believe I misunderstood this signal too. 8 volts on pin 8 means stop, but even now, I'm not sure where this is coming from, whether it's an external signal or coming from the IC itself. Anyways, that led me to follow the on-off traces, and more precisely to the on-off optocoupler. The optocoupler is a component to transmit the signal across primary and secondary of a power supply without an actual electrical link. So there is an LED inside, yes, those which make light, and a photosensor. The light shines onto the photosensor, and the photosensor acts like a transistor, allowing current to flow on the other side. To check whether an optocoupler works, I can measure the voltage drop across its pins, and you see here that I read about 2.2 volts. But when I operate the on-off switch, the voltage drop does not change, so maybe that is a path to follow. The other side of the optocoupler is wired to this little vertical board. The board gets IC from the smaller standby transformer we saw earlier and outputs 5 volts standby, which we know works fine. Also, the board gets the on-off switch signal from the actual switch I'm operating. That's it doesn't do anything else. Now, if I scope the on-off signal before it gets onto the board, I can see the signal when I flip the switch. So something seems to be wrong with this little board. Let's remove it and take a look at the components. But when I went to remove it, one pad came off and it looked like it was broken before. And guess what trace was that? The one going to the on-off optocoupler. Right, so let me resolder everything and fix this pad and test again before I go any further. When I went back to test the board, I applied mains and the power supply did not switch on this time. But when I flipped the on-off switch to the on position, it did switch on. Still only momentarily, but at least we fixed the on-off problem. At this point, I had a good feeling that maybe there was another cracked pad somewhere else, so I spent some time reflowing solder joints, but that did not help. I then removed and checked the only 2 small electrolytic capacitors on the primary. Those are critical for the controlling IC to function. The component tested did not highlight any issues. I replaced them anyways, but that did not help. I was clutching at straws now. I could not fully understand why the controlling IC was stopping, so I fitted the 2 bleeding resistors back in case it made a difference. It didn't. Then I spent quite some time checking and testing every single component I could find on the board, but I could not find anything wrong. I also ended up removing that vertical board we saw before, so I could inspect its components and surrounding ones, but with no luck. I encountered a couple of TL431 and made a little circuit on a breadboard to test them. They were both working. At some point, someone on the badcaps.com forum recommended that I remove the 115 to 130 voltage selector switch to see if that would improve on the excessive voltage at the capacitors. I had tested that switch before and I knew it was working, but I tried that anyways. And would you look at that, removing that switch, which was in the open position for 240 volts main as we have here in the UK, dropped the voltage across the bridge rectifier from 491 volts to 395 volts. Now the capacitors receive a much more manageable 197 volts each. 395 volts is still too high considering I do not see a voltage boost on the circuit, but definitely there was something wrong with the switch. Which is so weird as I tested the switch in resistance mode after removing it and it works fine. So I don't know what's going on here. The excessive voltage was likely why the bleeding resistors baked to death. With now only 197 volts, those resistors will have to dissipate 1.73 watts, which is much more manageable than the 2.64 watts we calculated before. But that was not the root issue here, and the power supply, unsurprisingly, still does not work. So I think I've reached a point in this project where I'm not sure I want to invest more time on this power supply. The reason is there's really nothing special about this power supply. As I said in my intro, the only special thing is that it belongs to a power computing computer and it says power computing on the case. But this is just an ATX power supply. This is nothing like the profile power supply that I fixed in this video, or like an Apple II power supply, which still can be replaced by a modern power supply, but it feels like you want to keep the original one. This is an ATX power supply, 200 watts, and from what I can see, this is also a cheap power supply, not only as the design of the power supply itself, but also the manufacturing of it, because every time I'm removing a component from this PCB, half of the times the pads are coming off with the component, so every time to put the component back on the PCB takes some time. Now, if you follow this channel, you know that I can be persistent with things, and I'd love to be persistent with this. I'm confident that if I keep staring at this PCB and looking at the datasheet and educating myself online on how this could work, I would eventually find a solution. The thing is, I really don't want this thing to walk around my workshop for months until I eventually find a solution. It really doesn't feel like it's worth these amounts of time. That being said, yes, you can install a standard power supply into the power computing, but ideally you really want to keep the power computing sticker. So I've decided to do a little transplant. I've got this random power supply, which is also very cheap from what you can see, but it should be a bit better than that one. It's a 500 power supply ATX, and the plan is going to be to transplant these into the power computing chassis. Now, from what I can see, these should fit, but it's not going to be a plug and play thing. It's not going to be just moving things around and it's going to work. So bear with me, stay with me, because it's not going to be boring, I hope. There's going to be some mechanical tweaking and also some electrical tweaking. But first, I've got this today. I don't really know whether it's working or not. Obviously, this is not brand new. So first thing first, let's test it before we disassemble and we take a look inside. To test the power supply, I used my digital load. I introduced it in my previous Apple profile video. It's a configurable digital load. I can dial in the current I want the load to draw, and that's it. I selected a 5 amp load to the 12 volts line, and I checked all the other voltages meanwhile. They were all fine. I managed to apply the maximum rated 22 amps to the 12 volt line, and the power supply did not complain. Besides that, I almost melted the cables. But when I went to test the 5 volt line, the power supply shut down at around 15 amps, when the label says it should do 27 amps. That's quite a difference. Yes, I did say it looked cheap. Now, for the use case, it should be fine though, as this is replacing a 200 watts power supply, so it's unlikely the 5 volts line is going to be pushed so hard. But that's not great. Okay, well, let's take a look at this thing inside and let's see what we can do to adapt it to the other one. Right, one thing I see in this one, there's a big choke, and I believe this is part of the power factor correction, not just because it says PFC on it. Now, let's compare this chassis with the power computing one. So that is great news. As you can see, the PCB is basically the same size of the existing one, and from what I can see, the screw holes are exactly in the same place. So the PCB is going to be like a direct transplant from this one to that one. There is space for the fan here, because obviously this new one has the fan on top, but there is a space here for the fan, and I believe it's going to fit no problem. The adaptation is going to be this choke here. Obviously that will need to be fitted somewhere, and I will have to find a place where to do it. So let me play with this and see how can I transplant everything into the old one. Now, to be completely honest with you, this power supply feels cheap. It's very light, the heat sinks are very thin. So yeah, it's basically an unbranded one. I think for what we have to do, this should be totally fine. Again, it's 500 watts and it's never gonna use close to its maximum limit, so it should be fine. But it's a cheap one. So what I'm going to do with this, I'm going to install the choke for the power factor corrector like here. This way there should be space for the mains coming in, and also space for the voltage selector switch, which is not going to be used by this one. This is single voltage, it is 230 volts only, but I'd like to put this back just for cosmetic reasons. And if I install this here, it would work, but that would prevent me from installing this back, and which means then you have the holes at the back, which you need to cover somehow. And so I'm going to do like this, which is, to be honest, as it was on the other one. There is plenty of space here, and that will give me space for the voltage selector switch, even though it's going to just be cosmetic. Right, I'm pretty happy with the outcome. The choke in here is perfect. It fits in there, so there's plenty of space, and that's going to be totally fine. Now, I still have a few things to do, including fitting the mains outlet. I'm going to fit the old one, as the new one has this little PCB on it, which is going to touch the components. We don't want to do that, so that's much more flexible. Then I need to change the plug at the fan, so it can fit in the existing socket. And then finally, what I'd like to do, I think I would like to remove the cables which are not needed. And most importantly, these only has 2 molecs and I need 4. So what I think I'm going to do, I'm going to remove the cables from the old power supply and solder them here, which probably is not going to be super easy because it's never easy, even though I can see the layout is pretty tidy here. So it should be just a matter of, sticking the cable in and solder it on the other end. So hopefully, finger crossed, that's not going to be too complicated. And that should be it, so let's crack on. And the power supply is back together. So let's quickly test that it works, there are no shorts, the fan is working, that the voltages are there, especially where I reinstalled the cables, I swapped the cables, and then I'll put together a motherboard and try and boot Windows and see, make sure that everything works. So let's give mains power in 3, 2, 1, go. Cool, I don't see a short. So let's power up in 3, 2, 1, go. And I can hear the fan. I got 5.1 volts out of this Molex here. Let's check that 12 volts is also there, and it is. And I can also check on the other Molex. I got 5 volts and I got 12 volts. So everything looks fine. We tested this before, there's really no need to do anything else. The fan is pretty powerful, so even though it's smaller than the other one, but this is noisier, so I'm not really concerned about airflow here. The other thing is, again, this is at 500 watts power supply, it's never going to be running 500 watts. So let me fish out a motherboard and I can just test it, make sure that all the voltages are fine, and we see a Windows desktop, and then we know that this is working 100%. So everything seems to be working fine, so I think I can call this project done. It's not done the way I would have liked to, as in repairing the actual power supply, but as I said, it really doesn't feel like worth a huge amount of time. I still had fun transplanting the new one into this one and do the mechanical adjustment and all the wires and everything, so I hope you had fun as well. Sometimes an easy project is also fun. You don't have to think too much, you just have to put things together and hopefully it does work. Well, I guess this is it for today. I hope you enjoyed this video. If you did, I would really appreciate a thumb up down below, and also if you could leave a comment, any comment, just to tell YouTube you like this video and someone is watching and the channel is alive. That would be fantastic if you can do it. For now, thanks for watching, I wish you a great day and I hope to see you again soon here on this channel for my next videos. Thank you very much and goodbye. Bye bye.